Hi, welcome to Chapter 20, Electrochemistry Overview Part 3, where we're going to talk about free energy and redox reactions and cell potentials under non-standard conditions. So free energy, if you remember, is delta G, and redox. So spontaneous redox reactions produce a positive cell potential, or EMF. So remember, last chapter we said for spontaneous, delta G had to be less than 0. And now we're saying that your cell potential, which is E, has to be positive, which is greater than 0. So remember, your E is your reduction minus your oxidation. But these E's here are for reduction. Okay? So note that this is true for all redox reactions, not only for voltaic cells. Since Gibbs free energy is a measure of spontaneity, or thermodynamically favored, positive EMF corresponds to a negative G. So a positive E corresponds to a negative delta G. So how are they related? They are related to delta G is equal to negative N Fe, where F is Faraday's constant, which is this number, which is really just the charge of 1 mole of electrons. And N is the number of electrons transferred according to your balanced equation for the reaction. So you see why when delta G is negative, that means E must have been positive. So let's go back to free energy, right? Under standard conditions, right? Do you remember what standard conditions mean? Standard conditions mean you have, if it's a concentration, it's 1 molar. If it's a gas, it's at 1 atmosphere. And you're at 25 degrees C, which is 298 Kelvin. So here we have our delta G formula. And this means if we plug in negative NFE for delta G, we get this formula here. And if we rearrange, we get something called the Nernst Equation. In the Nernst equation, we had to divide both sides by negative NF, and we get E is equal to our E at standard conditions minus RT over NF log Q. And remember Q from equilibrium. So what happens to E as the reaction proceeds? As the reaction proceeds, E is going to decrease. And we're going to see later why. So what is E at standard conditions? If we use the same metal for both electrodes, well then your standard E will have 0 volts. What is E if we use the same metal for both electrons? Well, this would be 0, and then E will just be equal to negative RT over NF log Q. Okay. So we've been talking a lot of equations. Let's put this into something that you can relate to. What happens to your battery, your phone battery, if you don't charge it? Well, after a while, it goes dead. Why does it go dead? Well, what happens is you are reaching equilibrium where Q equals K. Let's dive into that and see what that means. So let's assume we have a fake battery here that we made out of copper and zinc, and it's shown in this electrochemical cell right here. What happens to the concentration if we have 1 molar copper 2 plus in this cell here, and 1 molar zinc 2 plus in this one here? What happens to the concentration as this reaction proceeds? So as this reaction proceeds, this happens to be your anode, and this is your cathode. So your electrons are flowing from your anode to your cathode. As the electrons flow, zinc ions get deposited into the solution, so your zinc concentration will increase. As your electrons come into the copper here, they are going to attract your copper 2 plus ions and deposit more copper on this electrode. So your concentration of copper 2 plus decreases. So your concentration actually affects the voltage. As this cell keeps running, your voltage will be gradually decreasing, just like when you use a battery. It doesn't last forever, right? So batteries go dead because the voltage becomes too low. This happens when the concentration of the reactants becomes too low and the concentration of the products becomes too high. So remember our Q value where you have your products over your reactants. Okay, so if the larger the value of your Q, the longer your battery has been running. So it's closest to being dead. So if you have a very large Q, then your battery is almost dead. Okay, and when will it actually be dead? When you reach equilibrium, when Q equals K. So how are all of these things related? So we have delta G naught is equal to negative NFE naught. It's equal to negative RT log K. So here's how all three of these mathematically are related. Our potential of our cell, our free energy, and our equilibrium constant. So what happens if we're at conditions that are not standard? So remember, delta G is our standard delta G plus RT log Q. So if we plug in our NFE for them and divide, we get our Nernst equation right here. And sometimes you're going to see natural log, but sometimes you might see the regular log. So then they just basically insert the number that to convert from log to natural log to log. And then if you plug in your RT numbers here and your F value, you will get this constant here. So what happens if you have a cell set up with the exact same electrodes and the exact same solutions, but the concentrations are different? What will happen? Okay, so notice the Nernst equation applies that a cell could be created if the substances at both electrons are at different concentrations. And that is called a concentration cell. So for such a cell, your E naught would be 0 because your electrodes are the same. See, they're both nickel. Okay, so you see this one has a lower concentration, this one has a higher concentration, and you have some voltage. This one here, your voltage is 0 and your concentrations are the same. Therefore, as the concentrations are different, your E will not be 0. So let's get into the Nernst equation and concentration and just truly understand the trends, not so much calculating numbers, but understanding the trends. Before we could do that, we have to have a review of our natural log, which is ln. Remember, if you take the natural log of a number that is greater than 1, so a large number, you are going to get a positive value. So remember, on the multiple choice section of the AP exam, you can't use calculators. So it's important to know these facts about taking logs. If you take the log of 1, that's going to be equal to 0. If you take a log of a small number, a number that is less than 1, you're going to get a negative value. And you can see how knowing the sign of Q will tell you if the potential of your cell is going to increase or decrease by knowing the sign of Q. Okay, so remember Q from equilibrium, where it's just the products raised to their coefficients in the balanced equation divided by their reactants raised to their coefficients in the balanced equation. So what happens to the potential of your cell as your battery is being used? As the battery is used, you are producing more products. So your concentration of products increases and your reactant decreases. So this number becomes larger. So let's look at Q. So you have your products over your reactants raised to their powers. So if your products increase and your reactants decrease, Q is becoming larger. And the natural log of a number greater than 1 is negative, and this is going to be a larger negative number, and you're subtracting it, so it becomes a positive number. Oh, I'm sorry. The natural log of a large number is positive, and you're subtracting it, so then the potential of your cell is going to start to decrease. Okay, so what happens? Q becomes larger, so you're subtracting a larger number from your standard cell potential. Therefore, the voltage of your cell is going to decrease until it becomes 0. The battery's dead. How can you increase the voltage of a cell? So say you want to increase this. You need to make this term negative, so you have a minus a negative and it becomes positive. How do you get log of Q to be negative? You need Q to be less than 1. So you need Q to be less than 1, so therefore you need your concentration of your reactants to be greater than your products. And if we use a number line to compare E and Q, when Q equals 1, you are at standard conditions. If Q is less than 1, you're going to have a larger potential, a larger voltage. If Q is greater than 1, your voltage is going to start to decrease. So going this way, your voltage decreases. Going this way, your voltage increases. So let's apply this. So for the following reaction, for an electrochemical cell or a galvanic cell, here you have copper and zinc. With the voltage of the cell that would be set up with non-standard conditions, if what would happen to the voltage of this cell? So you have the concentration of your copper is 2 molar, your copper ions, and your zinc ions is 0.1. So remember, Q is equal to products raised to their power over reactants raised to their power. So what are your products? Remember, solids don't go in Q. So you're going to have that Q is equal to the concentration of your zinc, and there's just 1 divided by the concentration of your copper. So you have a number that is less than 1. So the log of a number that is less than 1 gives you a negative number, and then you're subtracting it, so you're going to end up with an increase. So let's look at that again. So here we're plugging in our numbers. We get Q is less than 0. We plug it into the Nernst equation. So this is now negative, a negative of a negative. So you're subtracting a negative number, which makes it positive, which increases E of your cell. So remember that the log of a number that is less than 1 is negative, so the voltage is going to increase. When Q is less than 1, you are further back from dead. Remember our number line. You're more further to the left. Thus, your voltage is increasing. If you don't remember the number line, let's go back. Here it is. Q less than 1, you are larger E. Okay? All right, let's look at the next example. For the following reactions, again, it's the same setup here. Would the voltage of your cell increase, decrease, or stay the same if you're given these concentrations now? So remember our Q is the concentration of zinc over the concentration of copper. So we have 3 divided by 2, which is greater than 1. So the log of a number greater than 1 is going to be positive. So you're actually going to be subtracting it. So you get that it's going to decrease. So here, you have Q is greater than 1. Plug it into the Nernst equation. This now here is going to be positive. So you're subtracting a positive, so you're going to decrease the voltage of your cell. So remember, when Q is greater than 1, the log of Q is positive, so the voltage decreases. When Q is greater than 1, you are closer to the dead battery, thus the voltage decreases. If you think of your number line, where you had, as you proceed this way, you're getting close to your dead battery. And remember, this is when Q equals 1. So the larger your Q, the closer you're getting to your dead battery. All right, let's look at this one now. Now they're giving you that the concentrations are the same. So Q would be the concentration of zinc over copper. Since this equation has a 1-to-1, we don't have to worry about exponents here. So it'll just be 0.5 divided by 0.5, which would be 1. Remember, the natural log of 1 is 0. So that means that our voltage should stay the same. So plugging it in. So this here, this term now becomes 0. So E is going to be equal to E naught. So when Q equals 0, the log of Q is 0. When Q equals 1, sorry, the natural log of Q is 0, thus the voltage stays the same. So, and be careful, guys, because this reaction is 1 to 1, we could just set it up like that. But if we had other numbers here, just because their concentrations are the same doesn't mean that Q is 1. So make sure you set up your Q expression properly. Okay, so for the following reactions for a voltaic cell, the galvanic cell was set up with the concentration of copper equal to 0.5 copper ions and the concentration of your zinc ions equal to 0.5. So the standard voltage is 1 molar. So how will this affect your cell? Will the battery last longer, shorter, or will it last the same length of time? So what are we comparing it to? If we were at standard, we would have 1 molar of our concentrations, but instead we have 0.5 molar. So since we have less, the battery will last a shorter amount of time. This is simply a limiting reactant question. The less chemicals you have means the reaction happens less, so the flow of the electrons will stop sooner, thus the battery will last for less time. And that is the end of part 3.